spec showing you how to fill in pages 4 and 5 on unit 12. So it's our last unit. This unit we're going back to some things we learned about in unit 3, atomic structure. So we're, instead of looking at how the electrons of atoms interact with each other to create different chemical reactions, we're now looking at changes that can happen inside the nucleus of an atom in what we call nuclear changes. And there are, the main process that is happening here is called radioactivity, which is the emission of penetrating rays and subatomic particles from atoms. And any isotope that is radioactive and therefore unstable is just called a radioisotope. Good. Now, radioisotopes are unstable. That means they decay, they break down in a predictable way. And there are 3 different types of decay, all release particles. There are alpha particles, there are beta particles, and there are positrons. For most of the time, there is also energy released during these processes in the form of gamma rays. Words alpha, beta, and gamma actually are Greek letters. So there are letters of the Greek alphabet, the first 3, and as they are those radiations, those types of radiations were pretty weird when they were first found out about. Scientists just gave them letter indications, but from the Greek alphabet. Okay. Then go ahead and use Table O to fill in the next section. Pause the video and then see whether you found the right answers. Okay, so you should have found in Table O that alpha particles can be shown as 42He or 42alpha. The He tells you it's a helium, the nucleus of the helium atoms. The 4 is the mass number, which also means it's the number of neutrons and protons together. The 2 on the bottom is the proton number, so the difference between them, the number of neutrons, is also 2 in this case. The only thing you could not find in Table O is what it can be stopped by, so just copy that in. And in general, the larger the mass of such a particle, the easier it is to stop it. So you need less cover to stop a larger particle because it simply interacts more with that cover. If you go down beta particles, you need aluminum foil or piece of wood. So that's already somewhat thicker, somewhat more substantial, because it doesn't have a mass, but at least it has a charge, so it can be interacted with by something like the electrons in a metal. And then if you go down all the way to gamma radiation, which neither has mass nor an electric charge, it's very hard to throw them off course or interact with them, and therefore it's very hard to block them. Good. Now, one of the really special features about nuclear reactions is that they defy the law of conservation of mass. If we measure the mass of the reactant and the mass of the products very, very carefully, with very good scales, then we notice that a tiny little bit of the mass, so little that we usually don't notice it in the mass numbers, but a tiny little bit of the mass is not conserved and is disappearing, completely disappearing, and changing into pure energy, according to Einstein's equation. E is energy, m is mass, and c is the speed of light. If you know nothing about the speed of light, you still know that it moves extremely fast. So if you square this really large number, you get a huge amount. And as you multiply that with the mass, that implies that even if you just use a small amount of mass in this process, you still get a huge amount of energy as you multiply it with this huge factor of c squared. Now that in turn means that if we look at different types of processes and rate them according to increasing amount of energy, we find that physical processes tend to use or release the least amount of energy. Chemical are somewhere in the middle, and nuclear processes release the most energy.